Welcome to the Deep Dive. And this is not just, a skim of the weekly news cycle. Consider this your high-signal intelligence briefing. It's built for the people who are actually in the trenches, the architects, the physicists, the deep tech execs who are steering the roadmap for artificial general intelligence. If you're tracking the entanglement frontier, this is what you need to hear.
That's right. We're here from the entangled state, and our job really is to find the signal in all that noise, to move past the market chatter and distill the few data points that signal a real fundamental phase transition. For too long, you had quantum and AI on these parallel tracks.
Studied almost in isolation.
Exactly. But today, they're convergent. And that convergence, well, it's the single most critical accelerator for AGI we have.
So our mission for this deep dive is very, very sharp. We're unpacking the most critical intelligence drops from the last few weeks, specifically the ones that are defining this quantum AI convergence. And we're going to figure out precisely how these breakthroughs, both in hardware and software, are compressing that AGI timeline. We want engineering realities, not just lab curiosities.
And the core thesis here, the one that I think demands a strategic reevaluation from everyone listening, is that the toy model era is dead.
It's over.
It's over. The conversation has shifted. It's not if quantum machine learning will have utility. It's how fast can we scale it? And we're seeing hardware fidelity climbing and climbing sharply. And this is the crucial part, without the scalability penalties that have historically just crippled other approaches.
That distinction is everything. Fidelity climbing without a scalability penalty. Because that's the signal, right? That's the indicator that we're finally moving out of the NISQ era.
The noisy intermediate scale quantum era.
And toward a genuinely manufacturable path to fault tolerance, a path that just dramatically cuts down the overhead you need for error correction.
So to map this out, we've structured this deep dive around two main pillars. Pillar one is the physical hardware breakthrough. We're calling it the silicon story. This is the engineering validation we've all been waiting for.
And pillar two, that's the architectural shift, the hybrid quantum machine learning story. And this is where we explain how that new hardware is being put to work by AI researchers right now to solve the biggest bottlenecks in training neural networks. So yeah, hold on to your classical registers. The data suggests the AGI runway just got a whole lot shorter, and it's time to start planning. Okay, so let's drill down into that first pillar, the huge shift in the hardware landscape. If we're looking for that smoking gun that proves a phase transition is happening, it has to be this announcement from Silicon Quantum Computing, SQC. They unveiled a multi-qubit, multi-register quantum processor. And look, if silicon spins weren't central to your roadmap before this, they really need to be now.
The weight of this announcement, it really just comes down to the numbers. The metrics are, well, they're startling. It's a fidelity surge that completely resets the benchmark for any solid-state qubit out there. SQC is reporting gate fidelities that are consistently between 99.5% and in some operations an astonishing 99.99%.
Okay, let's ground that for the executive who's focused on the application layer. Why does it jump from, say, 99% fidelity, which already sounds pretty good, to 99.99%? Why does that fundamentally change the entire game?
It completely changes the economics of fault tolerance. I mean, at 99%, the probability of an error compounding over a calculation is so high that your computation it decays almost instantly. You need a huge number of redundant physical qubits.
Thousands to one sometimes.
Exactly. Thousands of physical qubits just to create a single reliable logical qubit using error correction codes. But when you push that native physical fidelity to 99.99%, you cross a critical threshold. Suddenly, you need vastly less overhead, fewer resources, to get the same logical performance. And that reduction, that physical to logical ratio, is what makes fault tolerance achievable on a much, much faster timeline. It's the difference between needing a warehouse and needing a rack.
But let's add some friction here. I mean, we've all been tracking superconducting qubits from IBM and Google. We've been tracking ion traps for years. They've all put out impressive fidelity numbers. So why does this achievement from SQC with silicon spins demand this level of strategic attention, specifically from an AGI perspective? It has to be about fidelity at scale.
That is the critical point. That's the whole story. What's so fascinating here is that silicon directly attacks the Achilles heel of quantum scaling, which is that coherence versus scale trade-off. Historically, with other systems, as you add more qubits, the entanglement gets more complex, system noise goes up, errors compound.
And your fidelity drops.
Inevitably. It's been the main bottleneck holding back utility-scale quantum systems for years.
And yet, the core intelligence coming out of SQC seems to suggest they've, reversed that trend. The intel we're seeing confirms this highly counterintuitive finding that fidelity rates actually increased as they added more qubits to their multi-register processor. I mean, that's a foundational reversal of the problem that has haunted this industry for a decade.
It's not a trick. It's a validation of the underlying physics. The platform they're using, it's phosphorus-doped silicon spins. The genius of it is that they're leveraging the incredible natural stability and long coherence times of electron spins, but they're embedding them in this perfectly controlled, solid-state environment crystalline silicon.
Okay, walk us through the technical detail there. Why is a phosphorus atom stuck in silicon so much more stable than, say, a transmon qubit hanging over a superconducting circuit?
It comes down to atomic precision placement. They're using techniques like scanning tunneling microscopy lithography. So, unlike superconducting qubits, which are patterned at the micron scale where tiny imperfections create massive decoherence, the silicon spin approach lets you place individual phosphorus atoms, literally one by one in the silicon lattice. And because the coupling, the interaction between those spins, is determined by the precise distance between the atoms, they can engineer those connections with an unbelievable level of control. This precision just minimizes the crosstalk and noise, which in turn lowers the controlled overhead, and that's what lets them keep that high fidelity even as they add more qubits.
Okay, but every platform has a weakness. For the AI architect looking at a future with millions of qubits, the known Achilles heel for silicon has always been wiring. How do you route classical control lines to millions of these atomically placed spins without introducing a ton of noise and just losing the very fidelity you fought so hard to gain? That's the engineering problem.
That is the critical friction point, yes.
Ah.
And it's where their engineering solution is really compelling. SQC is tackling this with a mix of high-density local control fields and some very advanced multiplexing. By using on-chip integrated electronics, they shrink the distance, which shrinks the physical footprint and the thermal noise from the control lines. And because it's a solid-state environment, they can integrate more complex control circuits right next to the qubits, which lets them run parallel operations across the different registers. It's this architectural efficiency that's why the fidelity actually goes up. The system is designed to manage its own complexity.
So if the technical detail is the atomic precision, then the strategic implication has to be the manufacturing advantage. This SQC approach is CMOS compatible. That one fact means they can tap into the existing multi-billion-dollar global infrastructure of semiconductor fabs.
The CMOS compatibility is the existential accelerator. It's what blows the doors off the roadmap. It just completely bypasses the scaling limits and the massive capital costs that their rivals are facing. I mean, think about it. Superconducting systems need these incredibly specialized fabrication plants, these huge, complex cryogenic systems running at millikelvin temperatures. Silicon spins still need cooling, sure, but they can slot directly into existing, proven semiconductor supply chains. That dramatically cuts the cost and the time to market to get from thousands to millions of qubits.
It's a huge economic advantage. It means they're not just building a better qubit, they're building a better factory for qubits. They're leveraging decades of investment in things like ASML lithography and process control.
Exactly, and that positions the silicon modality for exponential scaling in a way that rivals just can't match right now. Not without completely reinventing their supply chains. Just the manufacturability alone probably shortens the time to get to a useful number of physical qubits by years.
Okay, let's bring it all back. What's for the AGI architects listening, what does a manufacturable path to high-fidelity, high-scale silicon actually mean for the training loops and parameter spaces they're dealing with today?
Direct impact on AGI is profound. This SQC breakthrough validates a realistic, engineerable path to millions of physical qubits with minimal error correction overhead. And that means we can start allocating resources today based on a firm expectation that fault-tolerant quantum processing is coming this decade, not the next one.
And that reduction in overhead, that lower ratio of physical to logical qubits, that's the budget line item that matters to an executive.
Absolutely. This single milestone in silicon shortens the fault tolerance runway by years. And for AI specifically, it means we're bringing practical quantum-accelerated neural architecture search NAS within reach in this decade. Classical NAS is just computationally prohibitive. You have this enormous search space of potential network architectures, different layers, connections, hyperparameters. Trying to search that space classically is a monumental, often randomized computational slog.
And quantum acceleration changes that whole equation because NAS is, at its heart, an optimization problem, isn't it?
Precisely. Quantum acceleration lets you efficiently explore these huge combinatorial search spaces that are inherent in designing AGI-class neural nets. Algorithms like QAOA or VQEs can navigate these high-dimensional landscapes to find the optimal architecture or the best weight initialization for a massive foundation model exponentially faster than just brute forcing it with classical methods. This is the mechanism that compresses the AGI development timeline.
Okay, so that silicon story sets a really robust hardware stage. Now let's move up from that physical layer to the architectural layer. This is where the quantum machine learning, the QML synergy, really comes alive and justifies that AGI acceleration claim. We're so far past the old dogma of separate fields.
Oh, that old dogma was always too simplistic. QC is for chemistry and materials. AI is for patterns and language. They were just parallel research tracks that might, someday connect. But today, those tracks have completely merged. The path to AGI, which is fundamentally a problem of optimization, of complexity, of efficient search, it runs directly through hybrid quantum classical architecture. We are in a state of engineering codependence now.
And that codependence is built on two intersecting mechanisms, and they create this self-reinforcing virtuous loop of acceleration. Let's break down mechanism one, which might sound a little counterintuitive to people focused only on AI stabilizing quantum.
Mechanism 1 is really elegant. You're turning one set of complex problems AI models into the solution for an even more complex set of problems, which is managing quantum reality. Neural networks, and specifically transformer models, are now the primary tool for decoding quantum errors and maintaining hardware stability in real time. The AI is the enabling tech that gives the quantum computer the coherence time it needs to do deep computation.
So in essence, the qubit is still noisy and prone to decoherence, but the AI decoder is like this constant, self-learning life support system. It allows the computation to finish by filtering out the noise faster than the noise can ruin the calculation. It's an immediate, practical use of AI that directly helps the quantum hardware.
And Mechanism 2 just flips that script. Quantum optimizing AI. This is where the QPU is being specifically designed and deployed to tackle those non-convex optimization landscapes that just stall the training of giant neural networks. I mean, think of the enormous computational cost of training a trillion-parameter LLM. We're talking hundreds of millions of dollars in compute just to nudge parameters in the right direction. QC is now being engineered to solve that specific bottleneck.
If we look back at the SQC fidelity news, we can see exactly why higher native fidelity is such an accelerator for QML. It lets you build deeper circuits for your quantum feature maps. So for an AI architect, what happens when fidelity is low?
Well, with low fidelity, your circuit depth is severely limited by decoherence, and that leads you straight into the infamous barren plateau problem. And this isn't just a quantum physics headache, it's a crippling problem for QML. A barren plateau means your optimization landscape just flattens out. The gradients you need to train the model, they vanish exponentially as you add more qubits. Your quantum model essentially stops learning no matter how much classical compute you throw at it.
So higher fidelity from a platform like SQC means you can run deeper circuits before decoherence kicks in. You're effectively pushing that barren plateau further out into a regime where it doesn't paralyze the learning process.
Exactly. And the technical implication of that is huge. Deeper circuits mean you can map more complex high-dimensional AI feature spaces. Think about the transformer embeddings in a cutting-edge LLM, which might have thousands of dimensions. You can map that into the exponentially larger Hilbert space of the quantum computer.
And once you're operating in that Hilbert space, which grows exponentially with every qubit you add, what's the functional advantage? We hear exponential speedup all the time, but what does it mean in practice for AI training?
It means we can use quantum phenomena like interference and entanglement to navigate those complex optimization landscapes much more efficiently. Quantum algorithms can give you quadratic or even exponential speedups in crucial steps like hyperparameter tuning or navigating the loss landscape. This is the mathematical tool that gets you past the vanishing gradients, the mathematical walls that keep stalling classical scaling laws. We're basically replacing random search with quantum-guided exploration.
And this brings us to what might be the most compelling argument of all, the promise of provable optimization. Current LLMs, they rely on massive brute force compute to get to a statistical approximation of reasoning. They're sampling, they're guessing, they're relying on correlation until they land somewhere close to a good answer.
And look, approximation is fine if you're just generating chat or marketing content. But for emergent general intelligence, for solving novel, high-stakes problems like drug discovery or logistics or autonomous systems, you need rigorous, provable optimization. The hybrid promise is to replace that brute force, statistical approximation, with provable optimization. And that fundamental shift is what allows a future AGI to reason exponentially faster and more reliably. When finding the optimal solution is accelerated by quantum mechanics, the model doesn't just get a little better. Its fundamental capability expands exponentially. It moves from prediction to prescription.
That changes the entire philosophy of AI development. We go from a paradigm of training models to just search through billions of plausible outcomes to training models to find the optimal path with quantum certainty. That's a massive philosophical and engineering jump.
It's critical, especially for scaling foundation models in complex, real-world environments where the search space is combinatorial protein folding, logistics, general planning. Quantum-enhanced exploration of these vast parameter spaces is really the necessary fuel for an emergent general intelligence that can handle new, unseen problems with high reliability.
Okay, let's go deeper into that first mechanism, AI stabilizing quantum hardware. And the best case study for this self-reinforcing loop has to be Google's recent drop on their Willow processor.
The Willow processor, it's a 105-qubit chip. That's a significant number of qubits. But the real insight for the AGI community is its performance. It demonstrates the ability to suppress errors exponentially as the qubit count goes up. This isn't just linear scaling. This is the first hard evidence of a fault-tolerant scaling curve.
So it's not just scaling the quantity of qubits, it's scaling the resilience of the whole system. But the real AGI hook, as we said, is the software they've married to this hardware, the introduction of AlphaQubit.
Right. AlphaQubit is a transformer-based decoder, and it was developed by DeepMind. And this is where AI architects should be paying very close attention. Think of it as a highly specialized, incredibly efficient neural network that acts as the quantum computer's immune system. Its core job is to identify and correct quantum errors, noise, crosstalk, decoherence in real time, with an accuracy that far surpasses traditional human-written error correction code.
So the very same technology, the transformer architecture that AGI architects are using to build large language models, is now being repurposed to manage the physical state of the quantum hardware that will, in turn, accelerate AGI development. It's the ultimate chicken and egg problem that solves itself.
It creates that critical synergy, that self-reinforcing acceleration loop. And why use a transformer? Well, the quantum error space is vast, it's nonlinear, and it's non-local. Errors don't just happen on one qubit. They propagate across the whole lattice in these complex correlated patterns. A classical algorithmic approach just struggles to spot those non-local correlations quickly enough.
And this is where the transformer's main strength, the attention mechanism, comes into play.
Precisely. The attention mechanism in AlphaQubit allows the decoder to look at the entire quantum state, all 105 qubits at once, and assign importance or attention to these subtle, correlated error patterns that might span multiple qubits and multiple moments in time. That pattern recognition capability, which is inherent to transformers, is what makes it so much more effective than traditional decoding algorithms.
So this ability for the AI to keep the quantum computer coherent, to basically keep it alive long enough to do a deep calculation, directly pushes the timeline forward for fault-tolerant computing. If the AI can manage the chaos, the compute time gets much, much longer.
Absolutely. Fault tolerance is the final barrier before we can really deploy these systems against AGI-level problems. The success of AlphaQubit proves that the solution to quantum chaos isn't just more rigorous human-designed physics, it's adaptive, self-learning AI.
And the proof is right there in the benchmark they provided. Google gave this dramatic contrast to show the sheer scale of the acceleration. The Willow processor, stabilized by AlphaQubit, finished a complex benchmark calculation in 5 minutes.
That same calculation, if you tried to project it onto the world's current fleet of classical supercomputers running non-quantum techniques, you're looking at an estimated 10 septillion years. Now, that number is so large it's almost meaningless. But what it represents is an exponential change in what is computationally feasible. It proves that certain deep computations, the kind you need to break AGI-level optimization problems, are already completely out of reach for classical scaling laws. It doesn't matter how many GPUs you buy.
Which means every AI architect has to realize strategically that the computational frontier for solving the toughest non-convex problems is no longer in classical silicon. It's decisively moved to this hybrid quantum classical plane where AI itself is keeping the quantum half of the equation viable. It's a total integration of hardware and software dependencies.
And this capability, the ability of AlphaQubit to handle the speed and complexity of error correction, it shows that AI is becoming foundational to the physics of computation. It's the practical admission that the physical reality of quantum mechanics, the noise, the decoherence, is just too complex for human-written code to manage effectively in real time. You need self-learning systems to manage the quantum state.
Okay, let's shift to mechanism 2 now. The QPU being architected specifically to optimize classical AI. This is where quantum hardware stops being a scientific curiosity and becomes a direct accelerator for your production environment. And we are seeing major players deliberately designing their hardware to attack classical AI bottlenecks.
That transition is absolutely critical. We're seeing hardware companies fundamentally split their roadmaps to go after AI performance metrics. IBM is a great example. Their strategy really illustrates this divergence.
Right. IBM's strategy is pretty sophisticated. They have the Loon processor, which is all about long-range couplers. That's the necessary tech for maximum circuit depth and, long-term fault tolerance. That's a long-term research track.
But the Nighthawk processor, that's the one every AI architect should be gathering intelligence on right now. Nighthawk is explicitly designed for what IBM is calling quantum advantage in near-term optimization tasks. It's not meant to be the final, perfect, fault-tolerant machine. It's a task-specific engine built to accelerate today's hardest AI problems.
And if it's task-specific, what architectural trade-offs did IBM have to make to get that optimization focus?
They're focused on optimizing connectivity and coherent stability. But just for the short to medium time periods, you need to run variational algorithms like QAOA or VQE effectively. So that means prioritizing reliable, high-fidelity 2-qubit gates and a physical geometry that favors the specific connection patterns you need for optimization problems.
And how does that focus show up in performance metrics that a deep learning team would actually care about?
Nighthawk can execute circuits with 30% higher complexity than its predecessors. For an AI team, higher complexity means you can run deeper, more sophisticated variational algorithms reliably.
And that lets you encode more complex feature mappings and explore higher-order correlations in your data.
And those algorithms are directly aimed at the training bottleneck that slows down all these massive generative models.
Exactly. Nighthawk is architected to target the exact type of non-convex optimization problems that are the source of so much computational expense in classical machine learning. We're talking about tuning the billions of parameters for deep generative models. Think of the latent spaces and diffusion schedules in systems like Sora, or the complex search problems in logistical AI like supply chain management or autonomous vehicle routing. You could argue Nighthawk is the first truly AI-ready quantum processing unit. It's designed for tangible ML advantage today, not abstract physics.
So it's about strategically offloading the hardest, most computationally frustrating part of training these huge models to hardware that is purpose-built to solve that specific kind of mathematical headache, the part where classical supercomputers just spend weeks getting stuck in local minima.
Right. And moving from hardware roadmaps to actual commercial deployment, the IonQ and Quantum Basel partnership is another clear high-signal indicator. It shows that quantum optimization is rapidly leaving the research lab and entering the commercial pipeline with a very focused application.
And this isn't some vague academic partnership. The mandate here is crystal clear. It's very tactical. Optimizing large language models. This is a direct, focused, and commercially viable use for near-term quantum resources.
They're deploying a very sophisticated hybrid workflow. They're using both quantum annealing, which is great for discrete optimization, and gate-based systems to go after the weight parameters of classical AI models. The process is called pruning and optimization.
For those not as deep in LLM architecture, can you explain why pruning is so important for making these models efficient and capable?
Sure, LLMs have billions, sometimes trillions of parameters. But many of those weights are actually redundant or have a minimal impact. But the classical system still has to carry their computational weight, which burns a ton of power and slows down inference. Pruning is the process of intelligently removing those redundant connections. The problem is finding the optimal set of weights to remove, the combination that keeps performance high while maximizing compression, is a massive combinatorial optimization problem. It's NP hard.
And that's where the QPU gets plugged into the workflow.
Precisely. By offloading that computationally expensive optimization step, figuring out which trillions of weights are truly necessary to the QPU, they are upgrading the intelligence infrastructure of LLMs. This helps models move towards more efficient and maybe even more provable reasoning, instead of just relying on the statistical sprawl of trillions of parameters. The quantum system finds the globally optimal pruning mask, which gives you a smaller, faster, and more accurate model.
And that's a direct commercial pathway that doesn't require a fully fault-tolerant, massive quantum computer right now. It's leveraging near-term quantum advantage to immediately improve the performance and efficiency of today's foundation models. That means immediate budget and latency benefits for users.
Now let's shift focus from optimizing the model to optimizing the data the model learns from. AGI is going to need extremely high-quality ground truth data that just doesn't exist on the web, especially data about physical reality like chemistry or fundamental physics. And this is where the Caltech and Riken experiment gives us a crucial blueprint.
They use what they called a quantum-centric supercomputer approach. They integrated a 77-qubit quantum device with the classical Fugaku supercomputer. This is the definition of hybrid computation. But what was the division of labor there?
The QPU wasn't solving the whole problem. It was acting as an exponential filter, a kind of quantum oracle. The 77-qubit device was used to rapidly identify the most important components, the high-signal subsets of a massive data matrix. So once those critical components, the complex high-dimensional correlations, were found and extracted by the QPU, the classical supercomputer, Fugaku, took over to solve the rest of the problem using classical high-precision methods.
That's a very efficient division of labor. The QPU handles the exponential complexity, the search space exploration to find the needle in the haystack, and the classical supercomputer handles the precise calculation once the search space has been narrowed down.
And this whole process is a blueprint for high-fidelity synthetic data generation. AGI has to model the physical world chemistry, physics, materials at a level of accuracy that current classical simulations just struggle with because of computational limits and approximation errors. Quantum computers are now being proven as capable of generating that necessary ground truth data to train future physics-aware AI models. So if the QPU is the optimizer for the training loop, it's also quickly becoming the data factory for the training set itself. That ensures the AI models are trained on data that is physically meaningful, which could prevent the kind of deep, factual hallucinations we see in current LLMs when they try to talk about complex science.
You're raising the fidelity of the input data, which in turn dramatically raises the potential ceiling of the AI's intelligence. It's a foundational step toward the level of scientific rigor that AGI will need to achieve.
Okay, our final source drop takes us to the absolute bleeding edge of generative AI, a new preprint on Arcsif about quantum latent diffusion models. And this merges variational quantum circuits directly into the latent space of diffusion models, which is the core tech behind tools like Midjourney and Sora.
This gets to the critical insight for achieving human-level intelligence: efficiency in learning from sparse data. The classical scaling law says that to get high capability, you need 1 trillion parameters trained on 1 trillion data points. But that reliance on brute force data volume is fundamentally inefficient and doesn't generalize well. Right. An AGI has to be able to learn from sparse data. A human can generalize after seeing, say, 5 examples of a complex object. Current generative AI needs thousands or millions. So how does integrating a quantum circuit solve this?
The quantum model can leverage the exponential nature of Hilbert space to encode complex feature correlations much more effectively than a classical model can. When you integrate that variational quantum circuit into the latent space, the compressed conceptual representation of the data, it can compress and correlate features exponentially more efficiently than its classical counterpart.
So the QPU is basically creating a more compact, higher fidelity, latent representation of the image or the concept.
Exactly. And this leads to a crucial advantage. It demonstrably outperforms classical equivalents, especially in few-shot learning scenarios when the training dataset is deliberately small. Because quantum systems can represent exponential amounts of information with just a linear increase in qubits, the model gets to high performance without needing these cripplingly large trillion-parameter datasets. So this compresses the AGI timeline not through faster optimization, but through a superior high-signal representation of the input data itself. It lets AGI learn smarter, not just harder.
That architectural shift is maybe the most profound one of all. If we can bypass the data volume requirements that are currently throttling the expansion of high-fidelity AGI, if we can make data learning exponentially more efficient, then the entire cost structure and time horizon for AGI just changes overnight. Okay, so we've covered a substantial amount of high-signal ground here. We've gone from the physical reality of silicon chips all the way up to the architectural potential of hybrid optimization. Let's try to synthesize the core takeaways for you, the deep tech executive or AI architect planning your next move.
I think the synthesis is simple, but it really demands action. First, the silicon breakthrough has validated the manufacturable path to utility-scale quantum computing. That's an engineering reality now. It shortens the fault tolerance runway by years and confirms that scaling physical qubits is possible this decade. And second, the hybrid architectural phase transition is moving AGI capability forward right now. It gives us quantum-accelerated exploration of these vast parameter spaces, and crucially, the promise of provable optimization is starting to replace our current reliance on brute force statistical approximation.
So in short, the acceleration is exponential, and the key bottlenecks, error correction, optimization, and data efficiency are all being successfully attacked by targeted quantum hardware. What should we be tracking in the immediate future to see if these trends hold? What's on the event horizon?
You have to watch for the full Nature publication drop that details the SQC multi-register device. That paper will have the fidelity metrics, but it'll also have the precise control mechanisms. And that will trigger peer review and competitive counter-announcements that will give us more non-proprietary insight into the real engineering margins of the silicon approach.
You should also keep a sharp eye on the persistent rumors about a Microsoft Azure quantum announcement, specifically about their topological qubit roadmap stability. Microsoft's approach is totally different. It's based on these non-abelian ennions, which are theoretically immune to a lot of local noise. If they announce a genuine, stable topological milestone, that throws another highly scalable, inherently fault-tolerant modality into the race, and that will intensify competition and accelerate integration across the whole cloud provider landscape.
And finally, track the pending capital expenditure releases from Sequantum about their new manufacturing facility in Australia. Their photonic approach is different again. It relies on room temperature optical gates. If their manufacturing ramp proves successful and they start announcing large-scale component delivery, it indicates massive industrial confidence in quantum scaling overall. It confirms the market is betting on several different paths to fault tolerance at once.
It's a dynamic, really transformative moment in deep tech. And given everything we've talked about, from alpha qubit stabilizing quantum states to Nighthawk optimizing generative models and quantum models learning from sparse data, it feels like the very nature of AI reasoning is about to get a fundamental upgrade.
Indeed. We started this deep dive with the premise that hybrid systems promise to replace the brute force statistical approximation that defines today's LLMs with provable optimization. That shift from high probability to mathematical certainty, it forces us to ask a fundamental meta question about the future of AGI. What does this shift mean for the inherent nature of AI reasoning itself? How will we define intelligence? And more importantly, how will we regulate or trust it when a model's core logic isn't just statistically sound, but is mathematically quantum provable? That transition from probability to proof is something for you to keep your states pure while you consider the strategic implications.
Thank you for joining us for this high-signal deep dive. We'll see you at the event horizon.